Okay, so 7.4 is the first official BC topic in the textbook besides Euler's method. Okay, and here's our objective. It's very simple. We've used integrals to find areas, and we've used integrals to find volumes. What else can we do with an integral? That's a good question. So it turns out that you can actually use it to add up anything you want. So one thing we might want to study is, let's say you have this graph. This is the tangent function. This is the fundamental period of y equals tan x. And let's just say you're interested in finding the length of the curve between negative pi over 4 and positive pi over 4. So this point right here is literally the point negative pi over 4 comma negative 1. And this is the point pi over 4 comma 1. And you want to know the actual distance, not between them, but traveling on the curve one point to the other. That's our objective. It's very simple. I want to know how long is the red segment, or the red curve. How long? That's a very simple objective. If I'm going to find a length, I need to compile microlengths. I need to add up tiny lengths. So the first thing I need to do is get a differential length, a tiny length, and then I will use integration to compile them. Okay? So the first thing I want to do is just visualize this as a collection of straight segments. Just draw a handful of these in here. Okay? Now this, if you add up the green segments, do you think that's going to really give you the length of the red?
Not exactly.
Not exactly. How would you get more accuracy? Smaller segments, more of them, right? So let the number of segments go to infinity. But right now, isn't it safe to say that the total length is approximately, at least, the sum of all these little segments? And we're going to call them delta S. Delta S, delta S, and so on. Okay? And each one is a little bit different from the others, right? So there are many of them. They all have their own size. So I'll put a little index here, a little sub-I. That just means delta S number 1 and delta S number 2 and so forth. And I ranges between 1 and n. N is just the number of little pieces I wish to use. It might be 10. It might be 2 million. Okay? All right. Okay, so what I want to do is draw a tiny diagram or a blow-up diagram of one of these DS's. Okay? So here is an expanded view of what I'm dealing with. This is my little delta S. It's a slanted segment, and it certainly is some amount of run and some amount of rise here. Okay, so delta X, delta Y, and there's a delta S. Now, what formula comes to mind when you see a right triangle and both the legs and the hypotenuse are all labeled? Pythagorean Theorem. Absolutely. So I'm going to write down the Pythagorean Theorem because that's the best tool I have for understanding a triangle. And this is sort of a triangle, the way I've constructed it. Okay, so here's a true statement. Delta x sub I squared plus delta y sub I squared equals delta s sub I squared. That's supposed to look like an I. Bless you. Everybody with me? That's just Pythagorean Theorem or distance formula. All right. Now, what else comes to mind when you see a run and a rise and a sloped line? Differential. Okay. What did Euler say? He said that slope times run is the same as rise. Yeah, delta y. Remember the table you made for Euler's method? You had a delta x column and a dy dx column. You multiplied those, and it gave you delta y, the rise. So another totally independent thing besides Pythagorean theorem that comes to my mind right now is just this. The slope is delta y sub I over delta x sub I. And the slope is that line right here is slope, right? And that is a tangent line in the approximations, or at least in the infinite approximation. Right now they're secant lines, but ultimately they'll be tangent lines later. So later on I'm going to replace m with dy dx, or f prime, you know? I'm going to isolate delta yi here so that I can put these two formulas together. All right. So I'm just going to real quickly convert this to read delta y sub I equals m delta x sub I. Just kind of cross multiplied it. And I'm going to stick that in right there for my delta y sub I. You can get ahead of me if you want. Okay, this is how far I got. Any questions so far? One less variable, that's nice. Anything factor out? We could factor out in delta x sub I squared, right? Let's do that. So we're going to have 1 plus m squared times delta x sub I squared equals delta s sub I squared. It's a little bit of algebra there. And ultimately, I'm not really interested in delta s sub I squared. I'm interested in delta s sub I. I just wanted the change in length of the curve. I'm interested in this slanted segment, remember. That's my goal, is to add them all up. So I'm going to square root both sides now. Yeah, don't worry about plus and minus. And you get, here it is, delta s sub I equals the square root of 1 plus m squared times delta x sub I. What is this? The actual length, what? It is going to be our integrand, you're right. But this is, and the differential's there too. There's a dx right there. We're going to turn this in infinite case in a second. But right now, this represents the actual length of that little thing. So it took a while to get it, but that was our objective, is to get the little length so we can integrate them to get the full length. Okay, now let's say that we take a limit, and we won't show formal notation here, but let's just say you let a limit go, n goes to infinity, right? What happens? Some things change, right? First of all, we don't call it delta s sub I anymore. What do we call it? ds. Well, they're all infinitely small and roughly the same, so we don't have to distinguish between ds1 and ds2. They're just differentials now. You see, they're all infinitely small and non-zero. What happens to m when we crush all the segments together? All the secant lines are just given away. All the little secant lines that connect to the 2 points of the curve then become what kind of lines? Tangent lines, right. All of those will be pressed to become the tangent lines at various locations. So what happens to m? Becomes dy dx, or f prime. Yeah. So this is going to become df dx, or let's put dy dx because that's what our book does. And it's squared. This does not mean second derivative. It means first derivative squared. There's a difference, right? And what happens to delta x sub I? It becomes dx. And if you want s, throw an integral bar on both sides. You see? So now we treat our integral as a operator, something we use whenever we need it. What does the left side become? S. Yeah, the full length of the curve. This is beautiful. So we found a way to do what we wanted to do. It was tough getting the little diagram figured out, and it was difficult isolating ds and all that. But this is it. the formula of the day, and I forgot the square right there, thank you. And of course, this has to happen between two meaningful values of x. Okay, you can't just find the length of a tan wave. The thing's infinitely long, right? So you need to have a specific section in mind, maybe -1 to 1 like I'm going to use. And also, please understand that hopefully the tangent wave is smooth in between the two values because you've got dy dx here. So if there's any like cusps or corners or vertical tangents along the journey, this won't work because it relies heavily on dy dx. And this needs to exist on the entire thing. So when is this thing good? When we have specific what? A specific endpoint in mind, right? And when dy dx what? Exists throughout the interval. In other words, the curve is smooth. Okay? So don't expect to use this, right smack through a corner or a cusp or break in the graph. You might want separate integrals. Okay. I will not rederive the second formula of the day, but you can also use this if you so desire. The derivation for this is exactly the same game, but instead of treating rise as slope times run, we treat run as 1 over slope times rise, and the whole thing becomes this. So this is great when you happen to have two y values in mind, and maybe your curve is given, instead of like y equals x squared, they give it to you like x equals y squared or something weird. Or if y is hard to isolate, you might want to use this second one. So know that you have both of these at your disposal. Can I move on and try finishing my example? So what did I set out to do today? I wanted to find the length of the tangent curve, specifically between -1 and +1. I want the length. And now I have an integral that can do it. Let me just check real quick. Does this thing look smooth in between -1 and 1? Nice and smooth? No vertical tangents? Good to know. Okay, it looks like it's ready to go. So we'll just do this. So easy. Just integrate between -1 and 1. Square root of 1 plus. Now, what is the integral, or the derivative, I meant to say, of tan? Because that's going to get in here squared, see? So what is the derivative? Sec squared, right. That's it. It's that simple. I don't think I can handle this without a calculator, because I don't think I know how to integrate the square root of 1 plus sec to the 4th. And I think I'd have to play around with identities for a very long time to get it. Let's just get out our calculator, type this as it's written, and it should give it to you. If your calculator is struggling with it, it usually means that there was a corner or a cusp somewhere along the journey, and it's getting stuck near that spot, and the processor is getting confused. Like the calculator is getting confused. But this one should be nice and smooth, and we are ready to go.
So should we type sec to the 4th x, or should we just do sec squared x to the square?
With your calculator, you can do sec to the 4th. You can even type that. Everyone else is going to have to type 1 over cosine. So you're going to have to be careful how you type this sort of thing. Yeah?
On the first graph you drew it, instead of having -1 and 1, you had -4 and pi.
You're right. What am I doing? My limits of integration, I wrote them incorrectly when I shifted slides. We're going from -pi/4 to pi/4. Thank you. Sorry. I was thinking of arctan. Okay. Let's get that integral going. And if your calculator's taking too long, just go from 0 to pi/4 and double it, because the symmetry will allow that. Pretty neat. Even if there's no antiderivative, the calculator can handle it, right? Did you get a number yet, anyone?
I'm getting an error.
If it's giving you an error, then it's having trouble somewhere along the way. I don't see any vertical tangents or anything, though.
I'm going to try this. I got error too.
Getting error?
Yeah, I'm still getting an error.
Okay, if you're getting an error, then that error is probably occurring near 0. So you could do this. We'll do 2 times the integral from 0 to pi/4. So we're just breaking it up into two of these purple pieces. See if it can handle it now. This is a problem. I mean, technology isn't perfect, right? See if it likes it better now.
I'm still getting an error.
And you're sure you're typing it right?
I mean, I tried both ways to see if the fourth and sec
I
squared
got
is
a
correct.
number. I got 2.55.
That's the correct answer. 2.55.
Did you do
Oh, no, hold on.
squared?
I got, yeah, that sounds right. 2.55, yeah.
Can you enter it in your calculator so we can see what you did?
So you want to see if I get an error too?
Yeah.
Sure. Let me see here.
Turn it on.
Yeah, I got it. What was it?
2.5.
Okay, so you do this kind of thing from the home screen. So we were going to do 2 times the integral, so math 9, of square root 1 plus, for the secant, I'll just type 1 over cosine x, quantity to the fourth, close the parentheses for the radical, comma x, comma negative pi over 4. Oh, we're going to go from 0. We're going to go from 0 to pi over 4. 2.555. Yeah, so truncate around, so you get 2.555 or 2.556. What am I doing? 2.555, or you can round that last digit to a 6. That's 2 pi. Change the limits of integration to negative pi over 4 and pi over. I think I wrote 1 and negative 1 here first time by accident. What did you use for limits?
Oh, I think I know.
Pi over 4, you got it? Are you in radian mode in your calculator?
I think I know why I was getting, because I was putting cos squared instead of cos x squared.
Oh, maybe to understand that cos square notation. Yeah, you have to do cosine of x, and then put that all in parentheses, and then put a square on the outside.
You put square or four?
Okay, so degree modes give us a different answer, because it doesn't understand what pi over 4 means. What else, what other issues came up? Any other issues? So how you type is important,
So you
but,
put to the four?
Yeah, I got it with, I got it.
yeah, just do the fourth. Put cosine x in parentheses, and then put a fourth power on it. Here's how I typed it. 1 plus cosine of x, no, 1 over cosine of x, and then all closed off, and then power 4. Okay, I'm going to work out one more example of this. This problem's a little trickier, but I think it will help you. Okay, so this one is actually number 22 from our textbook, and it's asking us to find the length of this curve here. Like that. Where this graph isn't really a function, it's kind of a 4-pointed star. And this is called an asteroid, meaning star-like shape. Okay, and they gave us the curve here. This is x to the 2/3 plus y to the 2/3 equals 1. Okay, so here's the problem in the book, as you can see. Okay, so they actually had to give us a bit of a suggestion on this one. This problem has some issues. First of all, it's not a function, right? So if you read that problem that I just put up there a second ago, you saw that they actually suggest we work in the first quadrant only, and they also suggested that we not find everything, but rather just part of this first quadrant curve. And then we can figure out how many of these we think would comprise the full asteroid and multiply by that. They're suggesting that we might want to do just this part, and that this part is literally 1/8 of the full asteroid. So there's one piece, there's another piece, there's another piece, there's another piece, and there's 2 in each quadrant, you see. So we're just breaking it down into 8 congruent pieces. We'll just work on the one piece. All right? They even were kind enough to tell us that this point is root 2 over 4, and this is, of course, x equals 1. All right? So we're going to basically find the length of that red. That's all. Okay, so we're going to be first wanting to find dy dx, because remember the formula relies on it. So the length, we'll call it s. S is supposed to be the integral from root 2 over 4 to 1 square root of 1 plus dy dx squared dx. So we will need to take the derivative. All right. Let's go ahead and isolate y, or I guess we could use implicit differentiation, but we'll have y's in our answer, then we don't need that. So let's go ahead and isolate y. We'll subtract the x to the 2/3 from both sides, like that. Oops, I wrote that wrong. X to the 2/3. And then we will take the 3/2 power of both sides, so that we have y equals 1 minus x to the 2/3, all to the 3/2 power. Okay, so let's find dy dx. Let me move my integral down a bit. Okay, so dy dx would be, bring down the 3/2, and take away a power, so now it's a half. Multiply by the derivative of the inside. So kind of ugly, but you can see that this 3/2 and this 2/3 cancels out. And we just basically end up with this 1 minus x to the 2/3 square rooted over x to the 1/3, like that. And this is dy dx, which is fairly ugly, but it won't be so bad after we square it, because it's going to get squared, you see. So let's stick it into our integral, and we have s equals integral from root 2 over 4 to 1 square root of 1 plus garbage squared dx, where garbage is our derivative. Square root of 1 minus x to the 2/3 all over x to the 1/3. And we have integral from root 2 over 4 to 1 square root of 1 plus. Now squaring this just removes the radical on top, of course, and makes this x to the 2/3 on the bottom. Okay, and this can be separated into two fractions, x to the negative 2/3 and 1. So this problem is actually working out for us. I don't know if we're going to need a calculator at all. So I just separated that into two fractions. Notice that the 1's cancel. And some of you catch my mistakes sooner than I do. I just realized something. I'm going to have trouble taking square root because there's a negative there. But it's because I made a mistake earlier. I'll show you real quick. It's really easy to find. It's actually right here. There's a negative there. So that was a negative. Actually, I take that back. That's not my error. If that was a negative there, it wouldn't affect anything. It still comes out positive. Oh, my error is right here. When I split this up, this is a plus. So this is a plus here. There we go. Sorry about that. Anyway, this is not a problem. You're going to basically have this integral. You're going from root 2 to 4 to 1. And this is basically 1 over x to the 1/3. Or you could just think of that as x to the minus 1/3. I'll write it that way. Dx. And you'll just solve this by adding a power. So adding 1 power gives us x to the 2/3. Put the reciprocal out front. Plug in the root 2 over 4 and the 1. We're going to subtract. So here we go. It's 3/2 times 1 to the 2/3 minus root 2 over 4 to the 2/3 So that's a little awkward, but we have 3/2 times 1 minus, and let's apply the square first. So you're squaring these, you get 2/16, which is 1/8. And then we are applying a cube root also. So this is a little bit of rational exponent nightmares stuff going on here. So 1 minus 1/2 is what's going on. So this comes out to 3/4. And that means that on the asteroid drawing, this first of the 8 pieces has length 3/4. So since there were 8 congruent pieces like it, you'd obviously just multiply this by 8. Okay, so the total length for the full asteroid is 8 times 3/4, which is 6. So one of the cool things about the asteroid is it looks neat, but also it has a really cool length. The length is exactly 6 all the way around. Pretty neat. So next time you want to take a 6-mile walk out in the wilderness, you might want to consider traveling the path of an asteroid. Just make sure you have your coordinates correct at all times and you're following the exact path of an asteroid. And let me know how you figure that out. That's the end. Now just in case you need one more example, I'm going to do one more example where you actually use dy integrals. So how would you do that? So the problem I'm picking from our book is this one, number 4, and it's x equals the square root of 1 minus y squared, and we're going between -1/2 and +1/2 on the y-axis. I'll copy it on the other page too. Okay, so it's number 4 from our textbook, and it is the equation x equals the square root of 1 minus y squared, and it's between -1/2 is less than or equal to y is less than or equal to 1/2. So they gave us definite y values, so it's probably wiser to use s equals, and then y goes from one value to another, and then square root of, instead of 1 plus dy dx squared, we'll use dx dy squared dy. So we'll keep our integral in terms of y only. Also, they isolated x for us, so it'd be easier to take the derivative of both sides with respect to x, or with y, than x. So that's just how we're going to do it. So I will need dx dy, and this side is 1 minus y squared to the 1/2, and we're taking the derivative with respect to y. So I just did basically what I did was I did a d dy right here and here. That'll give me dx dy, would it not? Okay, so we're going to start off by bringing the 1/2 down, taking away a power, multiplying by the derivative of the inside, and you do not need to do a chain rule here, really, because you're differentiating with respect to y and the functions in y. So if you wanted to do a chain rule, you would just have a dy dy, which is 1. So we're just treating this as if y is the independent variable, and we're differentiating with respect to it. So no need for chain rule really here. And this, of course, cancels, the 2's cancels, and you end up with just -y on top, square root of 1 minus y squared on the bottom. And this is going to get inserted into our function, right? This is dx dy, it goes right there, right into our length of the curve equation. So we're going from y equals -1/2 to y equals +1/2. We're doing square root 1 plus -y over rad 1 minus y squared dy. And we get s equals integral from -1/2 to 1/2, square root 1 plus, and this is y squared over 1 minus y squared. And if you do an LCD here, you might want to multiply this top and bottom by 1 minus y squared. Let me do that real quick. You end up with (1 minus y squared plus y squared over 1 minus y squared dy). These cancel out. And we get this. Negative half, square root of 1 over 1 minus y squared dy, or you could just write that 1 on top. Does that look familiar? Does that look familiar to you? Does this look like a familiar antiderivative? So you might recognize that this is inverse sine, and this is a y. So it's inverse sine y. So we can't always get that antiderivative figured out. Sometimes we just use our calculator. And if you look in the back of the book, they just give you the decimal on this. But this is going to give me, oops, these are from negative half to half. What is inverse sine of a half minus inverse sine of negative half? Well, this is just pi over 6 minus negative pi over 6. And that gives you pi over 3. So the back of the book will say 1.047. And I don't know why I'm using a squiggly. For this part, this is exactly equal to, the squiggle is reserved for our decimal approximation. Okay, so pi over 3 is the exact answer, and 1.047 is the approximate answer. If this was measured in meters, it would be meters, inches, then inches, etc. That's our first BC topic.